At the microscopic level, a haloalkane is a molecule living in a permanent state of high tension. It is inherently unstable, driven to the edge by the unequal relationship between its own atoms. The friction comes from the halogen atom. It acts as a massive electron sink. It hogs all the electrons in the partnership, aggressively polarizing the bond and leaving the carbon atom carrying a positive charge and desperate for a way to balance itself out. Because of this extreme internal stress, the haloalkane's fate is dictated entirely by the environment you drop it into. Under the right conditions, it will either violently eject atoms to save itself or stitch together with others to form massive new structures. This specific molecular vulnerability is what allows for the complex sequences found in organic synthesis. To force a breakup, chemists use an aggressive chemical catalyst called alcoholic KOH. Dropping our molecule into this environment triggers a subtractive reaction known as elimination. In this diagram, the alpha carbon loses its halogen atom, leaving a void. To stabilize, it steals a hydrogen from the neighboring beta carbon, forcing them to lock into a double bond. This forms a new alkene, while the expelled atoms become water and salt. This forced elimination is an intentional subtractive tool. It allows a chemist to engineer a double bond into existence, exactly where they want it. But the structure of these molecules can pose a dilemma. What happens if the alpha carbon is surrounded by multiple different beta carbons? Which neighbor does it steal from? The outcome is dictated by Saitsev's rule. The molecule will almost always choose to form the double bond in the most crowded, heavily substituted location available to it. This side-by-side comparison shows the rule in action. The major product forms precisely where the carbon has the highest number of surrounding carbon connections. The less crowded terminal option becomes a mere byproduct. These breakups are not random collisions. They follow strict mathematical laws, defaulting to the most stable structure. If we change the environment entirely, the rules flip. We place the haloalkane into a dry, water-free solvent called dry ether and introduce metallic reactants. When magnesium enters this environment, it behaves as an interceptor. Instead of ripping the structure apart, the magnesium violently wedges itself right in the middle, between the carbon and the halogen. This creates a highly unstable hybrid structure known as the Grignard reagent, named after the French chemist who first documented this interceptor behavior. The Grignard reagent is so ferociously reactive that a single drop of ambient water moisture in the air will cause the entire structure to collapse in on itself. But by keeping it dry, chemists keep it volatile. Inserting the metal turns the carbon chain into a loaded spring, primed for building complex molecules. If magnesium is an interceptor, sodium acts as a molecular matchmaker, driving a famous sequence called the Wurtz reaction. In this dual mechanism, sodium atoms enter the equation and simultaneously strip the halogens off of two independent haloalkane molecules. Stripped of their partners, the two isolated carbon chains lock hands, stitching together to form a single massive alkane chain. This mechanism applies universally. It works for straight chains, closed benzene rings, or hybrid connections. By utilizing metal reactions like this, chemists shift entirely into additive chemistry. They can take isolated carbon fragments and effectively weld them together into complex, custom architectures. Halogens function as precisely engineered chemical handles. They provide the specific entry point needed to manipulate a molecule's internal geometry and final destination. By studying these exact rules, learning exactly when to force a chemical breakup and when to initiate a metal hookup, early scientists were able to transition from observing nature to actively designing it. These principles allow for the macro-scale construction of the modern world. By lengthening carbon chains through matchmaking reactions or creating reactive double bonds through elimination, industry can mass-produce everything from the complex polymers in advanced plastics to the specific hydrocarbons in high-grade fuels. Organic chemistry provides the structural rulebook for reconfiguring carbon into the materials that sustain modern life. And no matter how massive our manufacturing gets, somewhere out there in a lab right now, a Grignard reagent is still running in sheer terror from a single drop of water.